My name is Savannah Lennon, and this is my Lab 4 for Physics 2211. Lab 4 is intended to have us, the students, determine the forces and energy acting upon a mass connected to an oscillating spring. The fundamental principles at work here are Newton's second law and the energy principle, also known as the first law of thermodynamics. This is an important concept to study because the ability to calculate the forces on a mass by a spring and the energies will allow us to apply these calculations and methods to other scenarios where it could be important to know the spring constant or the energies acting on the object. For example, it would be extremely important in order to ensure that an object makes it around a loop when pushed by a spring. In order to determine this, we would need to know the spring constant as well as the relationships between energy and position that would influence the object's motion. Here you can see the first two bits of my code, which include the givens as well as some of the calculations I included. The mass was given in edX to be 0.402 kilograms, and the initial position I used was determined by utilizing the tracker application. You can see how I determined this in the chart with the values from tracker that is just below the stated given values. And to the left of the screen, you see my results from calculating the spring constant as well as the relaxed length of the spring. In order to find the spring constant, K_S in this case, I used the formula K equals 4 pi squared times mass over T squared, which is derived from the formula used to determine the period of oscillation. In order to determine my period, which ended up being T is equal to 1.519, I subtracted the time where the oscillation was at a trough in my tracker data from the previous time it was at a trough. I repeated this 3 times and averaged the change in time over the number of times I did it, which was 3, in order to get the average period. And then in order to determine the relaxed length of the spring, L0, I used the formula L equals L hat minus mass times gravity over K, which is the spring constant, and that yielded 0.1269 meters. And L hat was given to be 0.7 meters according to the edX videos. To calculate each of the energies, I simply incorporated their respective formulas using the variables that were pertinent to the code. All of these formulas are visible on this slide. In the calculation loop, I changed my time to be 9.212 to match where my tracker data ended. After this, I set each of the initial energies to those previously calculated before incorporating Newton's second law into my code. The force of gravity is simply the object's mass times little g in the negative j hat direction due to the spring's positioning, and F net for the object is then the combined forces of both the spring and the gravity that is acting upon the ball. The application of Newton's second law comes in when updating the object's velocity and position, and in this case, we just need to take, for the velocity, the previous velocity and add F net over m times delta t, and then to update the position, we take the previous position and add the velocity times delta t. In order to calculate the energy changes, we again had to plug in the energy formulas and calculate the new energy at these positions, and then subtract those minus the initial that we calculated before. Here you can see the results from the update to the code I made. And in order for the data to work, we had to upload a CSV file that included the X and Y position data obtained from our tracker analysis. This then used the code to predict the position and graph it with the actual movement recorded. As you can see, the position graphs of the predicted and observed data are very similar, which ultimately indicated that we calculated the code correctly and that the energy graph is accurate for this model. The energy principle was indeed satisfied, which is evident by interpreting the results in the energy graph created by the code. First, the energy principle tells us that when added up, all of the energies in a system will equal 0, which in this case they did, which you can tell by the orange line, which is the total energy, staying at 0 the entire time. This indicates that no outside work was acting upon the system. And then by utilizing my tracker data, I also calculated the oscillation periods in the X and Y directions. They ended up being 1.519 in the Y direction and 1.646 in the X direction. These are obviously not equivalent. And this is most likely due to the fact that the period in the Y direction is displaying the up and down or natural motion of the spring, and the X direction is a pendulum-like motion, which ultimately leads to slightly different periods of oscillation due to the differing nature of the motion.